we won't get to all this today. I had my demonstration set up on a cart for today and Friday, and maybe even Monday. And I was in doing a demo in the other class, and my helper was being helpful and set it all up. But I'm just warning you, don't get disappointed. I'm not doing most of this today. This will be heat transfer, a lot of this. Maybe we'll do some for fun. It's all out here, so now we have the choice. Okay. Chapter 15, more on temperature, heat, and expansion. So, who remembers what temperature is? Specifically or generically? What do you got? There, he's got it specifically, because see, he took notes. Or you pulled it up on whatever. It's a measure of the average translational kinetic energy per molecule. There's a lot of qualifiers there. I really qualify it just because temperature is just a measure of one specific thing. But these molecules, these particles can have other types of energy. It can have more energy. It can move in different ways. They can be going faster. They can be going slower. But on average, the translational, how it's moving this way, not this way, not this way, not this way, how it's being displaced, translated, that has a certain speed, which gives it a certain kinetic energy. And you average all those particles together. The temperature is the average translational kinetic energy per molecule. Not all of them, just this, per molecule. That's temperature. Generically, we often say temperature is a measure of how fast the things are wiggling. That's how you can keep it in your brain. You got particles moving all over and they hit each other. And it gives you an idea for that. If they're going faster, then they're going to be hotter. They'll have a higher temperature. There are some temperature scales you're familiar with. And probably some you're not. Let's see, we got Celsius. It's the most common in the world. And 0 to 100 degrees. They came up with that because that's when water freezes and boils. Freezes at 0, boils at 100. It was nice, it was convenient, 0 to 100. Fahrenheit, many of you in America are familiar with, and the rest of the world is annoyed with now at this point, but it works. It was built based on the same idea, freezing and boiling. This is in your book too. 32, we say freezing is 32 degrees Fahrenheit, and boiling is at 212 degrees Fahrenheit. You can see there's more degrees on the Fahrenheit scale in between here than in the Celsius. So one good thing about Fahrenheit is it has a smaller resolution. Per degree Celsius doesn't tell you quite as much as per degree Fahrenheit, because you can fit more degrees in there. So 1 degree change is a smaller change in Fahrenheit. That's one use. This was useful too because it, like everything else in the English scales, inches, foot, miles per hour, it was kind of based around the body and what we were familiar with. And so people could relate to it easier. But now we're moving to metric, and Celsius divides it up nice and evenly into 0 and 100. There's another one that scientists use that most people aren't familiar with, and that's the Kelvin scale. The reason we use it in science is because we don't want it relative to something else. It's an absolute scale. The others aren't absolute. They're based on boiling and freezing. Kelvin is an absolute. Freezing and boiling goes from 273 to 373. And I'll note, if you say 273 Kelvin, you don't say degrees. You say 12 degrees Celsius. Thank you, Pauline. I appreciate it. You'd say 32 degrees Fahrenheit but on Kelvin, because it's absolute, you say 273 Kelvin. When people say degrees, they don't know what they're doing. So this goes down to 0. This is absolute. Some of you might have heard of absolute 0. That's 0 Kelvin. That's the end of the scale. And what that represents is if the molecules are getting colder, they start moving slower. They got less average translational kinetic energy per molecule. When they're at 0, it doesn't mean they actually do a dead stop. They're still moving a little. They can still have this motion. They can still have this motion. They can still have energy, but they have no available kinetic energy to give up anymore. Hence the temperature's 0. That's absolute 0. And nothing has reached that yet. We've gotten really close, but nobody's reached 0 yet. It's kind of like an asymptote. Who knows if we'll ever get there. Why did they choose 32 on Fahrenheit? I used to know this historically, and if we Wikipedia it probably has the history. I don't remember anymore, but it was the guy testing his own, body temperature, and he tried to melt ice and boil water, and this is where it all fell. Why he picked 32? I think it fell on 32 and 212 because he related it to his own body temperature first, and I can't remember the details. Was in there somewhere, and that's where the others fell. No, it's not a time reference. It's interesting historically, but I can't remember the details. All right, there's your temperature scale. So, thermometers. They measure temperature. Here's your classic thermometers. They have a bulb down here full of fluid. Historically, it was mercury. Now we often use alcohol. There's other ways to do it. And when things heat up, those molecules start moving around. They start pushing on each other. The pressure increases. It expands. And they expand it up a really skinny tube. And it stretches on up. And then they calibrated it. By how much this expands, how many degrees it went up. If it gets colder, it contracts, less pressure, and it doesn't push it up as high, and it goes down. Thermometers are clever. You have to do the scales differently depending on the material because they expand and contract differently. Thermometers, though, can only measure their own temperature. We're like, oh, what's the temperature in the room? It's been in here a while, right? You look, and that works because all the molecules hitting this, the bulb at the bottom, they come to equilibrium. Let's say the room's hotter than the thermometer. Which way will heat flow? From hot to cold, naturally. So yeah, the internal energy will lessen for the air. Its temperature will go down because it's giving up energy. Where does that energy go? It's conserved. Goes into the bulb of the thermometer and it heats up. And shows it. So it does a good job when you got a lot of air. But let's say you put one drop of water, one cold drop of water on the bulb. How's the bulb, the thermometer, going to affect that one cold drop of water? Who's hotter, the thermometer or the drop of water? Probably the thermometer. So heat will flow from the thermometer to the drop. If you had enough water, this would drop to the temperature of the water. But it heats up the drop too. If you don't have enough of it, it could be an inaccurate reading of what the temperature of the drop was initially, what you really wanted to know. In other words, by measuring the temperature of the drop of water, you've affected the temperature. I mean, most people don't do this, but I'm just trying to prove a point that thermometers only measure their own temperature. But we use them to measure the temperature of other things. But they do affect what they're measuring because heat is transferred. Here's a version. This just has green water in a bulb. Let's see, Karate Kid, right? Warm my hand up. If I touch the top of the bulb, what do you think will happen? I heard force liquid down. Good job. Because now the top is hotter. So it gets the air inside moving, and yeah, that exerts pressure on the green water and pushes it down. So in a sense, I can measure the temperature of my hand in a sense. And as that cools back off, the pressure in the water will go up. What's actually pushing the water up in this case? So very good. The atmospheric pressure. The air in the room gets in here and pushes on that surface and forces it up the straw. The pressure here drops because it's cooling. This pressure will be greater. Differences in pressure move fluids. Good. Here's a different thermometer. Let's see. It's about 72, 69, 73, 71, 86. Infrared thermometers we use a lot more. We'll discuss this more next chapter. But anything with a temperature gives off radiation. Infrared light generally. That detects the infrared light. And based on your temperature, you give off a certain frequency or wavelength of light, and it tells you what that temperature is. Just because you have a temperature. If you got colder, you'd give off a different wavelength or frequency of light, and this would know. Here's another one. I like these. Anybody have one of these? Or seen them before? They're called Galilean Thermometers. Basically, they have colored fluids inside the spheres, and then a clear fluid outside. Generally, none of it's water. But it's great because it's a thermometer. Yet it uses buoyancy and density. The way you're supposed they calibrate them is the lowest floating one tells the correct temperature. Let's see, this is 75, so maybe it's a little hotter here under the lights. Plus I calibrated this when I first got it, and it was a little off. But it's more of a, knick-knack toy thing. But how's it work? Okay, if the room's hot, that thermal energy, heat is transferred to this. What would that do to the liquids inside the spheres? They're going to expand. They're going to fill up more of the sphere. So you got a sphere full of some fluid, and if it takes up more space, what happens to the density of that whole sphere? It increases. It's filling up more of it. You got more fluid taking up that space instead of just air up here in a fluid. There'll be more fluid and less air. More mass in the same volume. The density will increase. But its overall volume staying the same. There's not enough buoyant force and it'll slowly sink. That's how they calibrate these. The type of fluid, the density of this fluid, the density of the fluid it's around, size of this volume that's being displaced, and the expansion of this, how heat transfers in and out. It's clever. Looks like it's heating up because it's going a little further. But with density and buoyancy, you can tell the temperature with one of these. Does that make sense?
Oh, that's not very accurate then, because one says 75, and that's relative.
Yeah, these two, I think, that's 75. The next one is 80, so there's a 5-degree difference anyway. So it's somewhere where you could trust between 70 and 80. You can make them more accurate, but then they'd cost a lot more. Most people have them as decoration rather than an actual thermometer. But they do work. All right, let's transfer some... No, not yet. Not that. Yes. All right, hope this works. I have to admit, I've never done this inside. Sparkler. It's great when you can have a sparkler. Do you guys get worried when sparklers get close to you?
No, not really.
How come? Say that again? There's little mass. Yeah, I'm using this as a demonstration between temperature and heat. Yay, physics! Woo! So, are these sparks hot? Absolutely. They have a large temperature. They have a big average translational kinetic energy. But if they land on you, does it hurt? No, because there's not much internal energy there. So the individual, per molecule, they're hot. But there's not much internal energy because there aren't that many sparks. There aren't that many molecules. So this is kind of a demo to differentiate that. There's a big difference between internal energy and temperature. Which way does temperature go? Hot to cold. It's a difference in temperature, not a difference in internal energy. Something can have a whole lot more internal energy than something else, but that doesn't mean heat will flow from it to the lesser. It's temperature that matters. Now I got another one. I always try to find an excuse to do this demo. Cornstarch. It doesn't have to be, it's just cheap and easy. A lot of powders work. I grew up in Kansas, and we had a lot of grain silos. And my father, I remember one day, worked near one. Well, he worked at a chemical plant, and he came home telling us there was a big explosion at one of the grain silos, miles away from him, but they felt the percussion wave. Things rattled because it exploded. And grain isn't flammable when it's packed together. But if you can spread it out so that there's more surface area per volume, you can see those individual grains, oxygen can get to them, and then they can burn. So they can get really hot, and they burn. They might not have much internal energy there, because there aren't that many particles, but the individual ones now can burn. And if you contain that explosion, the pressure increases, and you have a bomb. That's what can happen in grain silos. So I'm going to take the cornstarch and spread it out. So you can get an explosion. Okay, tell me, do I got it all over? Hey, that's probably the least messy one I did. That's fun at parties, in the backyard. So it spreads out. There was a lot hot temperature there in there. But relatively speaking, there weren't that many particles. They were able to burn now, but not much internal energy. Now it smells kind of good too. Is that a fire extinguisher? No, this thing? No, it's a propane torch. So I blew it out, and as they spread out over the flame, they could ignite. I have to use this for that flame as opposed to this, because this is too weak and it gets blown out. Maybe I've done it with a little straw full. That works, but that's more fun. I do have a fire extinguisher though, right here, just on the other side of that wall. Actually, that's the first fire extinguisher I ever had to use to put out a fire. I've used fire extinguishers a lot for various physics demos, but there was a fire right here. My first year I worked here, one of the professors burnt a demo. That was exciting. I thought I was fired. But I put it out and all was well. Okay. Heat, usually represented by a Q, that's the transfer of energy. It's like work. Objects don't contain heat, they don't contain work. But you can do work on something or have work done on you, you can transfer heat to or from. We've already discovered that those are proportional to a change in temperature. Heat does not flow unless you have a difference in temperature. We've mentioned a few times how much mass of the thing matters. If you have a whole lot of water over here and a little bit of water over here, and this little water is hotter, Heat will flow from the little hot water to the big warm water. But the big warm water has more internal energy, so it won't affect its temperature as much. The transfer of heat, the transfer of heat won't be as big because you have a lot of it. It'll have a small effect over here. So how much of the matter you have also matters. So mass matters. And then the last one is this new term. Specific, that's not right. Specific heat capacity. That's the C. That is what material you have. It's what's the heat capacity of this type of material you're using. In other words, steel versus water. They absorb and give up heat differently because they're built differently, their structure. So C takes that into account. This actually, our guide to thinking, MC delta T, is this. This is our friend. In most of thermodynamics, I use that more than anything else. If you want to know how much energy is transferred? Heat? Well, you look at these three things. The bigger the temperature difference, the more heat you drive. The more mass you have of something, the more heat it can contain. In other words, that little bit of water versus a big amount of water. The big amount of water can have more heat, more internal energy. It's capable of transferring more heat. And water has a huge specific heat capacity. It can absorb a lot of energy. Whereas metals tend to give it up quickly. Water can retain it for a while. You've probably noticed that if you boil water on your stove in a metal pot, you turn it off and you set it to the side, the metal can cool down fairly quickly. But the water can retain that heat for a long time. That's because water's specific heat capacity is a lot larger. And since we have dealt with inertia a lot, that's how I like to think of this one. Thermal inertia. Remember, inertia was resistance to change in motion. The specific heat capacity is your indicator of whether some object material wants to resist absorbing or giving up thermal energy, heat. Heat will be transferred. That's transferring thermal energy. And I should pause. I tend to use thermal energy a lot. In this class, thermal energy and internal energy are the same. Temperature is a measure of the average translational kinetic energy. Everything else, including the kinetic, is internal energy. But often people call that thermal energy too, when they're dealing with how much can be transferred in the form of heat. So I just apologize and warn you now, if I say thermal versus internal, same thing. So water will resist heating up as much as metal. Again, let's take them at room temperature. An empty metal pan and a pot of water. And you put them on the burner and apply the same heat to both. In other words, we're trying to put in the same amount of thermal/internal energy into both. So Q is the same. If you have the same amount of water as you do metal, which one will have a larger change in temperature? Got one vote for 2. There's 60 of you. If you put the same transfer of heat, same energy into both, and you have the same amount of both, which one will heat up first or get hotter more quickly? In other words, a greater change in temperature. Well, it'll depend on this. Which one has a higher specific heat capacity? Who has a bigger thermal inertia? Who will resist wanting to change its temperature as much? Water. So heat will still go into the water. Heat still goes into the metal. But the metal's temperature will go up faster because it has less thermal inertia, a smaller specific heat capacity. Does that make sense? Are you sure? Good. Specific heat capacity? This is how I remember it. No fancy unit. If you rearrange that, C is Q over M delta T. This is energy. So joules. Mass is kilogram. And this is Kelvin. So nothing fancy. Yeah. Okay, if that makes sense, and the same amount of energy is going into both of them, but the metal heats up faster, where's the energy going in the water? Why is it not getting hot as quickly? Energy, we're putting energy into it. Where's it going? Oh, I know, you got an idea. Into bubbles? When it starts to boil, yes. If it gets to boiling, then that energy is going into changing phase. Absolutely. But before it gets to boiling, we're still putting energy in. Where would that energy be going? There you go. Internal energy. It's not going into translational kinetic, or its temperature would be going up the same. So it's not making a move around like this as much, as quickly, but that energy is going into things like this, and this, and this. So it's still gaining energy. Energy is conserved. You transfer heat in, it absorbs that heat. It's absorbing the exact same amount of energy as the metal. But the metal has less thermal inertia, so it affects its temperature faster than the water's temperature. Is that clear? You guys are ready for spring break. Good, okay. So now let's do this one. Or maybe I should light it and then let that settle. I'll do this one first. All right. This has metal here and wood here. They have different specific heat capacities. Which one do you think has the larger specific heat capacity? Wood. Wood resists heating up as fast. This has a larger thermal inertia and resists the change. So I'm going to input heat. I got paper on here. And if I input the heat, that's no fun. That'll take forever. Let's do it with this. What's happening? The paper's burning on the wood side. Why? I'm putting the same amount of heat on both sides, right? Transfer of heat. This has thermal energy. It's hotter than this. Heat's transferring from hot to cold. I'll just hold the wood. The paper burnt. So where did the energy go on this side? Paper. Where did it go on this side? The metal. The metal has a higher specific heat capacity. Lower specific heat capacity. So it absorbs and changes more quickly. That's where the energy is going on the metal side, not the paper. On this side, though, the wood must have a larger specific heat capacity than the paper. The energy is going into the paper and burning it. You can actually boil water that way. If you do it slowly enough, not over a raging fire, but I've boiled water in a paper cup. That's what this balloon's for. I think you know what will happen if you take a balloon and put it over a flame. Heat was transferred quickly. Air has a big heat capacity. It resists changing. The rubber in the balloon has a lower specific heat capacity, less resistance to change. So it absorbed that thermal energy until it bust. Water balloon. This balloon's full of water. Where's the energy going? Obviously not into the balloon, or it would have popped by now. It's going into the water because the water has a huge thermal inertia. It has a big capacity to absorb heat before it changes its temperature as much as the balloon does. So the water is taking the energy. Have I even... Yeah, it's starting to burn, little brown spots. It gets darker. This flame is a cleaner burning flame. If you did this over a normal candle, you get that soot collecting on the balloon. There's some more. See the soot? The candle's hot. It hits here. The energy is transferred into the water, which cools the flame particles, and the soot condenses and settles on the balloon. But the energy is going into the water because it has a higher heat capacity. And good. It didn't pop. I don't have to clean it up. So let's expand some things. It's called a bimetallic strip. There's two types of metal on it. One's, and I don't even remember what they are, so sorry. But this side has one type of metal, this side has another type. They're different. They have different heat capacities. So they will increase their temperature at a different rate. What do things do when they increase their temperature? They expand. So one of these will expand faster than the other, but they're connected to each other. It should curve. And it doesn't matter which side I hit. Yeah, it's a bimetallic strip. Heat it up, heat's transferred. One, the energy goes into increasing the average translational kinetic energy. Temperature goes up, they're moving more. They expand more than the other side. It's going in more into internal energy. There's a difference, and so yeah, this side expanded more because it's going to curve more. This side expanded less. How can you use this? There's just some practical applications to these. We used for many, many years. What's that? I'll give you credit. Switches. They can act like switches to allow us current to connect and then release, connect, release, connect, release. So something that's intermittent, like a blinker. Or what was most common were thermostats. Let's see, let's plug this one in. 12 volts only, deal. If it got hot in the room, it would heat up the bimetallic strip, right? It would bend. And if it bent enough, it could make or break an electrical connection. Usually it bend, and it would connect. Turning on the air conditioner. Then it cools off. The bimetallic strip doesn't bend as much, breaks the circuit, turns off the air conditioner. Ingenious. So let's do that with this. I have two bulbs connected to this bimetallic strip. So let's turn it on. 12 volts. Right now it's connected to the white bulb, if you couldn't tell. Let's heat up the bimetallic strip. It bends. Oh, it's not connected to anything. It got hotter, it bent further, and now it's connecting to the red. Allows current to go to this side. As it cools back down, bueno. Speed it up. It'll work. As that cools, it'll relax, bend back to the other side. Oh, now it's not touching either side. Ooh, feeling a little woozy. It'll eventually go back, connect to the other side, allow current to go through there. All because of this transfer of heat, and that things have a different thermal inertia, specific heat capacity, so they react differently. There we go. So things like, if you live near a body of water, say the beach, you got sand and you got the water. And you're in the sun all day basking, this is nice. Which is going to heat up faster, the sand or the water? Good, the sand, because it has a smaller thermal inertia, less resistance to changing its temperature. Good, absorbs that heat. Okay, now the sun goes down, and it's not absorbing energy anymore, it's giving up energy. Who's going to cool off faster? The sand, for the same reason. It has less resistance to change, so it'll give up energy quicker also. The water will stay warmer longer than the sand will once it heats up. But the sand will heat up faster than the water. All right. This is fun. I used to hate thermodynamics. I won't lie. Now I think it's cool. All right, now water's fun. Oh, before water, the two right in front of me. And then we'll do water. Yeah, good. Good. Give you time to sink in.
So, thermodynamics, I don't know how to word this, but that's the force that acts on air that causes it to rise.
The force that acts on air causing it to rise? Thermodynamics is this transfer of heat thing. How things absorb and emit thermal energy and heat transfer. It's dealing with heat, thermal energy, is thermodynamics. If you heat something up, thermodynamics is involved. So hot air versus cold air. But the change it has on it because of expansion changes its density and how much space it takes up. Now that goes back to buoyancy. So the actual force that makes it go up would be the buoyant force. Warm air has a bigger buoyant force than cool air because it's less dense. It's taking up more space. And so it'll rise. So thermodynamics causes it. And in that case, buoyant force then will make it go up. Does that help? Yeah. See, all this stuff's connected. Forces, fluids, thermodynamics. I hope you guys are appreciating the world around you a little better this semester. Yeah? Even if it's still not completely, understandable, you at least are you noticing it more? Curious when you're at home or doing things, like, hey, that's physics. I should ask Adam about that, and then you forget. But write it down, email me. These were just two other quick ways of doing the same thing. These are not bimetallic. It's all one material. But they're twisted. Think of it as one long piece. And if you heat it up, it should expand. Well, the only way it can expand is by getting longer. Since it's coiled up, it'll make a bigger coil. This can work as a meter. Say this is, 10. Whoop, it's hotter. It would work. And as that cools, same way that way. So that was an easy way of making a little thermostat or something. This one's requires a little more thought. Same materials, iron, a solid sphere, and a loop. It fits through the loop. Barely. If I heat the sphere, what should happen? Transfer, yep, it'll heat up. It'll expand and it won't fit through the loop. What if I heat the loop instead of the sphere? Do you think the ball will go through? So the hole will get bigger? Side view is, the ring, the loop looks like that. I'm going to heat it up. Will the whole thing get bigger? Will it get small? Will the outside get bigger, but the inside get smaller? They're both made out of iron. That one's a little trickier for most folks. What if we took this and opened it up and heated it? What would it do? Yeah, it would expand. It would get longer. Let's just see what happens. Let's do that one first. Now it's iron, so it heats up quickly because of its low thermal inertia. But there's a fair amount of mass there, so I got to do this a while. Okay, it fit through before. It still fits through. So the whole thing expanded. The ring just got bigger, including the hole. Let's heat up the sphere now. Okay, let's see what happens. Still fits because they've both expanded. Now I'll have to come back to that, and we'll see what happens when this cools and that's still hot. So we've done two cases. They both expanded, so we're back to where we started, just bigger. But the hole itself gets bigger when it expands. I'll have to wait to finish that up. In the meantime, I'll start with water. Oh yeah, Patricia. This? I heated it up and it expanded, so it got longer and was trying to uncoil. So as they heat up, they expand, which makes the coil get bigger, and it rotates. A way you can use this idea to measure something. Let's just try it again. So, can you guys hear me over this okay, or should I just wait? Oh, go ahead. Except I can't hear you.
They always expand the same direction. Why don't they expand?
It will a little. But things expand along their length. If they're longer, more. We'll see if the ring is cooled enough. I don't know. There we go. So now the ring is closer to back to where it started, and the ball has expanded so it can't fit through the hole. I won't leave it that way because then it'll get stuck. I'll never get it apart. But that's how I've had nest bowls in the kitchen, nesting bowls, and they stuck and they were glass. I couldn't get it out without breaking it. What did I end up ultimately doing? Most of the time it works. I heated up the outside one, so it expanded. And I put ice in the inner one, so it contracted, and it came out. It didn't. I also added some Windex. It had silicone in it, and that helped lubricate. But so water is a very special chemical. We're very grateful for it. It does something a little different than most every other material. And your book explains this really well. I will test you on it, so I encourage you to review there also. And this will probably be the first thing I discuss, Friday again, because we'll run out of time. But water, we already said, expands when it freezes. Most things don't. If you decrease the temperature, then they give up heat. Heat is transferred because there's a difference in temperature. It's cooling off. You know that. You put something in the freezer, it's hot, the freezer's cold. The internal energy comes out of your food, your pizza, right? And it warms up the freezer, cools off your pizza. And if you could keep doing that, it would get colder and colder. It would freeze, and it would keep contracting. Water contracts when it gets cold. Water molecules, they get closer and closer together. They contract, they slow down, they're not hitting on each other, so they contract as it gets colder and colder. Ice, when it gets cold, it contracts. And those locked water rings get tighter and tighter and tighter. Ice contracts when it gets cold. It expands when it gets hot. Water expands when it gets hot. But the transition between the two isn't like most things. Water gets colder and colder, contracts, 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 but then it starts turning to ice. And ice takes up more space than water. And so it expands when it transitions. Once it becomes ice, it'll keep contracting. But during that transition, it does the opposite of what we'd think. So if you thought of a bunch of water molecules, they're free to slosh around. I'm approximating here. If these are water molecules, you can see they can pack tightly together. And they will as it cools off. Ice, though, forms a crystalline structure. I just have to look at these hexagons, or I draw them funky. Like that. When water's completely frozen, it looks like this, roughly. Don't tell your chemists. I didn't draw it right. They're hexagons. Can you see this is going to take up more space? That's the expansion we're talking about, which means it's less dense. It'll float in water, ice. You guys knew that. No shocker. So as water cools, it contracts. It contracts. But at some point, some of the ice is lost. Remember, they're not all exactly the same temperature. They don't all have exactly the same translational kinetic energy. Some can be going faster, some can be going slower. On average, they have a certain temperature. The ones that have slowed down enough will freeze first. And they'll start forming this. And you'll have a combination of slush. Yeah, that's not a technical physics term. Slush, this ice-water slurry. And so, if you have some of this and some of that, the combination will be less dense than just ice, just water. These can pack tight, 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 but now some of them start forming the crystals, and it starts expanding again. And then once all of it's that, it's expanded. We're grateful for that. Think about if ice didn't float. What would fish do? The whole pond would freeze. So this is great. The water at the top, it's closer to the cold air temperatures, right? So the top water will lose energy faster than the lower energy. It's kind of insulated by this big thermal inertia, specific heat capacity of the water. So some of the water on the top will lower its temperature. It'll be colder at the top than the bottom. What will happen to that cold water? Cold, hot. Cold water, hot water. It's kind of like cold and hot air. It sinks. Cold water contracts. It's now more dense than the warmer water below it. It'll sink and settle to the bottom. Now the new warm air is on the top, and it gets chilled. It lowers its temperature. It contracts. It becomes more dense, and it sinks. And so on until all of it gets cold. Until all of it gets to 4 degrees Celsius. That's the magic number. You thought 3 was a magic number. Yes, it is. Yeah. Who remembers Schoolhouse Rock? Okay, thank you. No, 4 degrees Celsius is the magic number for ice and water. A pond will not freeze until all the water becomes 4 degrees Celsius. It can't. But at 4 degrees, that's when the slurry starts happening. Some of the water starts turning into ice, and it starts re-expanding. And if it expands, it becomes less dense. Rises to the top and keeps getting colder and colder and becomes the ice. But only at the top will it become ice. If you see a pond frozen over, you know the bottom temperature must be 4 degrees. The top can get colder, but the bottom has to be 4. And that's how fish can survive. They don't get frozen. So review that in your book. We'll go over it more. Patricia has a question, and we'll end. What's what? 4 degrees Celsius in Fahrenheit? I don't know exactly, but 0 is freezing in Celsius, 32 is freezing in Fahrenheit, so it's roughly 36-ish